Okay, let's have a look. So I want to show you a way to do like kind of a harder rational root theorem problem. This is the one we started yesterday, right? So
I'm
just get us all up to speed here. So remember, the rational root theorem tells us that if a polynomial has rational coefficients, which this one does, right, then all of its rational zeros have to be built from fractions, where the numerator is going to consist of factors of the constant, so all the factors of 16, and the denominator would be factors of 3. Okay, we'll take the positive and negative versions of all those fractions we can build. So you always kind of start off by looking at what could the denominator be. So it can only be a 1 or a 3 in this case, right? If it's a 1, that's convenient, and those are just integers, and those are easy to run through synthetically and check, right? Let's get all the, let's click everything closed here. This is one where I trust me, you're going to want to see this. So then we came up with what are all the integer factors of 16, positive and negative integer factors of 16. So that's 1, 2, 4, 8, and 16. And then if we divide those by 3, which new factors do we get? Well, we get 1/3. We get plus or minus 1/3, 2/3, 4/3, 8/3, and 16/3. So there's a huge list for us to troll through and see which ones work. But the good news is we may not need to go very far, right? Because this is a 5-term polynomial. We don't have any strategies for a 5-term polynomial. The only strategy we have is this one, is just to use the rational root theorem, right? But if we can get a hit on this, we can find a factor. What is this going to drop down to? If we can find one factor, the polynomial that's left over is going to be what degree?
Third.
It'd be 3rd degree, wouldn't it? Right? We'd end up with a linear factor times a cubic to make up this 4th degree polynomial that we started with, right? Well, if it's a cubic, then that means at most it could have 4 terms, right? And so we're going to start running into some familiar territory where we could solve this without having to use the rational root theorem. We could use one of our strategies. Quick review. What are our strategies? If we have a 4-term polynomial, what's our strategy for factoring that? Grouping. Yeah, good. So we'd split it into 2 groups. We'd group. Oh my goodness, thank you. That'll probably work. If it's just water, it'll be fine.
All right.
So we got 4 terms we would group. 3 terms, what would that be?
Are you recording?
I am recording, yep. Quadratic form, right? We try to break it into packets where we can treat it like a quadratic form, a trinomial. 2 terms.
Easy.
Sum or difference of cubes or a difference of squares, right? We've got a few patterns we could use there. If we can just get it through one level, then we're good, right? So we got to addition a bunch of zeros though, and so if you were to do this traditionally with like the regular synthetic division bracket, you'd have to keep rewriting that thing over and over again, and that would get tiresome. So I'm going to show you another way to do this. This is what you might call tabular synthetic division, okay, where we're just going to kind of work down vertically, and we can try a lot of different candidates very quickly and easily. So let's start with the easy ones. We'll start with the easy ones down at the low end of the spectrum, right? So we'll start with the 1s and the negative 1s. And as you go through this, you'll kind of see also that you can kind of establish some trends. Like if we're trying positive zeros and 1 doesn't work and 2 doesn't work even more, and 3, sometimes you can start to realize, okay, this is going in the wrong direction. So I can already predict that none of the positive zeros as I get bigger have any chance of working, and so we can just kind of ignore those. Yep.
Can't we right away eliminate all the negative terms? It's going to have to be positive.
Why is that?
Because if any of them if they were all negative, then you would end up just adding a bunch of terms together.
Because you're seeing that the odd powers are negative.
Yeah.
Yeah, you probably could, except that last one's not. But probably, because that last one's not, see, that's an even term and it's a different sign. That's good. That's a good observation. But I don't think it's going to work necessarily. It's because you've got one that's off that pattern, right? But that's the kind of thinking you can start to kind of do too, though. Yeah. So let's try +1. How about? So we'll try positive 1. Now what are my coefficients going to be that are going to go in here? So this is like this is equivalent to saying, here's my synthetic division bracket. Here's the remainder box. See what I'm saying? Oops, actually, hang on. The remainder box would be
Below that.
right there, right? You get the idea? And this is the number that's out front, okay? So what are the coefficients? 3, negative 2, 47, negative 32, and negative 16, right? And then we're just going to check a bunch of these and see what happens. Okay, but we're going to kind of combine steps. Like we know that below, so now consider this to be the bottom of the synthetic division bracket. So we know we're going to drop a 3 down, right? And then we multiply 3 by whatever number's out front. So 3 times 1 is 3. But instead of, we're going to do the addition in our heads. It's just addition. So 3 plus negative 2 is 1. Good. So we would have gotten a 1 below the bracket, wouldn't we? We won't bother putting that extra number in there. We can do the addition in our head. 1 times 1 is plus 4. Right? Oh, whoops, that's 47. So 1 times 1 is 1, plus 47 is? 1 times 48 is? Plus negative 32.
16. Wow.
And what do you know? Okay, we get a 0 right away. Okay. Does that make sense? Okay, so we got one. I didn't really want to get, I forgot what the answers were. I didn't really want to get one that fast, right? So now we could, maybe we'll do one more probably. So now we get this down to where we know we got a 0. So these are our new coefficients, right? So we have some options here. We could just continue on. Now we could just drop another line down here and start over, right? And now we don't need this last column anymore, right? This one's, because now we've only got a 4-term polynomial, so this becomes our remainder box. And we could just keep going if we wanted to, right? Now this time we notice that all of the coefficients are positive, right? So are the positives going to probably work here? They can't, can they? Right? All the positive values, like if I were to plug in any positive value, you see that these numbers down here are just going to keep getting bigger. They're never going to go to 0, are they? Right? Everybody get that?
Yeah.
Okay. So we know that we could cancel out, at this point we could cancel out all the positives. Right? Yeah, that's right. Okay. And we could just try some negatives, or we could also just try to solve this thing, right? Now, there could be 4 terms there. Do you think factoring by grouping is going to work? Let's just try it. Let's try it and see what happens. So we got 4 terms, 3, 1, 48, 16. So if we go to the next page, we end up with, we have 3, so we're going to get a 3. Whoops. So we get a 3x cubed, then we had a 1. Then we had a 48 to 16, is that right? Yeah, I would claim that you can already see this is going to work. How do you know it's already going to work?
Because those 2 numbers on the right are, it is.
I agree with that statement.
Because the ratio 3 to 1 is the same as 48 to 16, right?
Whoa.
So you can already kind of see that because those are proportional, right? That you know, you can already tell the grouping is going to work. Right, so if we go to this page here, so what is the greatest common factor from the first group? Leaving me with +1, good. And then if we do a plus, So we know we need to get a 3x plus 1. We already know we can't, right? Because the ratio of 16 to 48 is 1 to 3. So what do I factor out? Okay, and so look what we get. So we end up with
Oh, like the race band. Nice job.
3x plus 1 times what?
X squared plus 16.
Okay. So we already got it factored. And then we can find the zeros from that pretty easily if we wanted to, right? Set those equal to 0. So we're going to get negative 1/3, or we're going to get plus or minus 4i, right? If we set those equal to 0. Okay, so we could have, if we wanted to, though, like let's just say, hypothetically, let's say we didn't see that pattern, right? We could keep going with this. We would just start additioning other numbers. Like we could plug in -1, right?
You only do it if the remainder was doing that. If it wasn't, you'd have to do it the same original answer.
Yeah, right. So if we hadn't paid her on that first one there, right, we would have to just keep on trying numbers. Okay. If we try -1, let's go through this. So we drop down to 3. -1 times 3 is -3 plus 1. -2 times -1 is 2 plus 48. It's not going to work, is it?
Oh, that'll work.
That's not going to work. So we can cross off -1. I got to leave myself a little more room.
You just rinse and repeat.
Exactly. So the -1's off the board. We could try -2, right? So if we try -2, we'll just cross that guy out and go again. So we bring down the 3. 3 times -2 is -6 plus 1, -5, right? -2 times -5 is 10. So that's not going to work either, is it? Right? That's actually getting worse. We're getting bigger numbers here, and we need smaller numbers, right?
Right.
So we know that's not going to work. What do we get?
2/3.
We get 58, so it's way too big. Okay? So we could probably pretty quickly establish that, you know, like if we try -4, that's going to be even worse, isn't it? Right? We can kind of see a trend. 3 times -4. -12 plus 1 is -11 times -4. 44, we're getting even bigger numbers. Okay, no good. So maybe we can see that you know, these negative big numbers, we don't even need to try. So we can skip over to the fractions, right, and try the negative fractions. So we could try something like -1/3. And just see what happens there. So I drop the 3 down. Well, that looks good, right? -1/3 looks good because we're undoing that 3. We're going to get an integer result back. -1/3 times 3 is -1 plus 1, 0. 0 times anything is 0 plus 48 is 48. And we got it, didn't we? Right? -1/3 times 48 is -16. So we got a 0, right? Okay, and so that would help. Now we would know at this point, we would know that, okay, 1 was a 0, -1/3 is a 0, and now we got something quadratic, right? So all we'd have to do here is just 3x squared plus 48 equals 0. Just solve that, which is easy, right? You get the idea? Okay, so you can find lots of different numbers with this tabular integration, and it gives you a chance to kind of see what the trends are too. When you don't have to do so much writing, you can just try them out and see, okay, no, that's not working. We're going in the wrong direction. So let's move on to the fractions or something, right? Okay. Get the idea?
Yes.
Okay. Good work. Right. Get questions answered.